table, and what are the various inputs, okay, and then how does that express the functions. Let me just, if I can just quickly scroll back to the one that this is something like a truth table, okay. So P and Q expresses the various input combinations, and then in this particular truth table, it has one, two, three. It has 6 different functions. Okay, it shows the truth of 6 different functions. But of course, minimally, a truth table will show just one function. So you can imagine P, Q, and let's say not P. So that not P is actually the function. Okay, so this is an example of a truth table. Okay, going back to our slide again. Okay, so truth table is actually one possible way. Another way is actually to show graphical symbols. That means we draw all the gates, okay, all the gates connected to each other, and then that is we show the circuits. All right, and then of course that combination of circuits will then express the overall function that we want to show. Yeah. The third way is actually using Boolean equations. That means, F equals to A, B, not C, la, 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 and all that. So using those, algebraic symbols, A, B, C, or P, Q, R, or whatever. So we use that to express the functions. Okay. So these are 3 ways of defining the function or defining the circuit or whatever you want to call it. Okay. So how do we implement all those Boolean functions? Now, there are several alternatives to actually express a function, okay? And what we are talking about here is a standard way, okay? A standard way of expressing a function. So one of these standard ways is what we call sum of products, okay? Sum of products. Now, what does this basically mean? Sum here meaning we want to add, right? You want to add. But of course, in a Boolean expression, we are not actually adding. What we are doing is actually we are doing an OR. Okay, we are doing an ORing. Okay. And in product, what do we mean by product? When we do normal mathematics, product is actually we are doing we actually doing multiplication. All right. What we want to achieve is multiplication. But of course, in Boolean algebra, we are not doing multiplication. We are doing ending. We are ending. Okay, we are doing an end. All right. So sum of products will eventually look something like this. So we are having, let's say we're talking about 3 variables, A, B, and C. So it will look something like this: A, B, C. So ABC is actually the product, okay? And then another one here, let's say A, not B, not C. This is another product, okay? But now we want to sum it together, okay? We want to sum it together. So it will look something like this. So it's A and B and C, or A, not B, not C. All right, so this is what we call sum of products. We are summing the products. Okay, the ABC is actually a product. It's multiplication, but it's actually ending. We're ending. Okay, and so on and so on. So you can carry on like this. It not A, B, not C or something. So it's sum of products. Okay, all right. The other standard way of expressing a Boolean function is product of sums. Okay, so then it's now the other way around. So product of sums. Okay, so the sums here will be, let's say, A or B or C. Okay, and then products, right? We're going to AND it. Let's say not A or not B or C, for example. Okay, and so on and so on. This can go on. So it's actually a product or ending of sums or ending of ORs. Okay, ending of ORs. A or not B or blah blah blah. Okay, so this is product of sums. So this is what we call the canonical or standard way of expressing Boolean functions. You can either choose product of sum, sum of products, okay, sum of products, or product of sums. Okay, so that's the idea behind the expression of Boolean functions. So let's say from a truth table, okay, now this is an example of sum of products. So from the truth table itself, for example, here we have A, B, and C and a function f. So basically what we do is we collect all the ones, okay? So if you notice that in this function, we have one here, one here, and one here, correct? Okay, so we choose those functions that are true, okay? And then we pick up all those variables, the A, B, and C's, and then we OR them. So in this case, if you notice, those three functions consist of, see the A, okay, let's say look at the first one. Let's look at the first one here. Okay, the first one here. The A is a 0, the B is a 1, and the C is a 0. Okay? So when the A is 0 means it's not A. Okay? When the B is a 1 means it's a B. When the C is a 0 means it's not C. Okay? So therefore, we arrive at this one. Okay? So this one is this one. Okay? So not A, B, not C. Okay? And then we come to the second one. The second one, not A, B, C. So that means A is a 0, B is a 1, and C is a 1. All right? And then the third one, A, B, not C. That means A is a 1. Okay, if you can see, A is a 1 here. Okay, A is a 1, then B is a 1, and then C is a 0. Okay, so we pick up all those function f that is true, and then we can AND all the variables, okay? And then after that, we OR all the groups, all right? So that's how we express sum of products from the truth table. Okay, I hope that it's simple enough, clear enough, okay? From the circuit point of view, okay, so remember again, we can define the combination circuit in three ways, remember? So we have the truth table, the graphical equation, graphical symbols, and also the Boolean equation, right? So here we have the truth table, we also have the Boolean function, okay? And then we also have the gates, okay? The gates. So again,
Doctor,
if, yes?
maaf, maafkan saya. Can you redefine the combination of circuits? Combinational circuits. What are they?
Combinational circuits is already in the slide here. Yeah, see the combinational circuits is how we combine a few gates together to express a function, and that's
To
it.
express a function. So when we
Yeah, to express.
make multiple gates together, and we
Yeah, a few gates together to express a function. Okay, so like for example, if you have if you look at the bottom of the slide here, f equals to not a b not c, or not a b c, or a b not c. So how do we achieve this function? Is actually basically assembling a few gates together, or to assemble a few operations together. So we have the AND and NOT and OR operations. And all these operations are implemented in the form of gates, right? So as I was mentioning to you, we can express all these combinational circuits in three ways. One is the truth table. So this truth table expresses a combinational circuit as well. Of course,
combinational circuit of F. The F is the combinational circuit, right?
yes, correct. I mean the function of the circuit. Okay, but of course, when we say circuit, we think of the something physical. Okay, we think of something physical, but of course, there are conceptual ways of representing the circuit as well. So this truth table expresses the function of the circuit. All right, this Boolean expression down here also expresses the function of the circuit. Okay, and eventually, all these gates, the diagram of the gates here, will also express the function of the circuit as well. Okay,
so
that's the meaning of combinational circuit. Sorry.
So F will be 1 if all of the three things on the right are right, or it can be true on the first not A, B, and not C, and it can be not and it can be true when not A, B, and C.
Okay, so to answer your question, we look at the truth table. So remember the F is actually the output. Okay, the F is the output. The F is the output of the circuit, right? So
Okay.
F will only be true if A is false, B is true, and C is false. Okay, so for example, so in this case, if A is zero, okay, let's just look at this one. Let me just erase this whole thing.
Take your time.
Okay, from this function f, we notice that if this is true, then function will be true already. Why? Because all these are ORs, right? So even if this is false, and if this is false, and if this one is true, the function will be true already. Okay.
Yeah.
So let's just look at only this only this term here, not A, B, and not C. Okay, let's just look at F equals to not A, B, and not C. Now, this one will be true if A equals 0, B equals to 1, and C is equals to 0. Correct?
Yes.
So what? Okay, if A is 0, what is not A? If A is 0, what is not A?
1.
A will be 1. Okay? Now, if B is 1, what is B? Also 1. If C is a 0, what is not C? Not C is a 1. So and if we add it together, then function f will be true. Okay, so that's how we define the truth table like this. Okay? So similarly
Okay,
for the other terms.
I got the first one. I got the first one. If it's one of them, one of these combinations are true, then F is true. We don't need to look
Yes,
at
correct.
them.
Yeah. So
Okay.
since it's and ORing is ORing of those terms, any one of it is true, then function f is true. Okay. Now
Okay.
obviously the first one, the first one here, when A is 0, B is 0, C is 0, F it will be false, right? F is going to be false. Why? If A is 0 and B is 0 and C is 0, obviously it's going to result in a false. Okay, so that's how the expression works. All right.
Okay.
Okay.
Thank you, doctor.
No problem. Okay, so I want to explain this diagram. So this diagram basically uses three different gates. We have the NOT gate, AND gate, and OR gate. Why? Because in the function itself, you will notice that there is where's my pointer? There is NOT here. See, there's a NOT. There's also all the ANDing. Okay, the product. We want to do product of sums. Remember, so all the products will be caused by the ANDing, and then we also have the ORing. Okay, because we are doing the summation of all the terms. So we have AND gate, OR gate, and NOT gate. Okay, now let's look at the first term. The first term, I hope it's self-explanatory, but I just want to just to be sure that you all get it. So look at the first term, not A, B, not C. So that will actually go into this AND gate. Okay, that AND gate receives 3 inputs because in each term there are 3 variables. All right. So the first input comes from here, which is a not A. Okay, understand? So the first input is not A, and then the second input to this AND gate is see where it connects. Where it connects. It connects here, so it's a B. All right, and then the third input here, it's connected here, right? And that belongs to this NOT gate. So that means it's actually not C. So here is not C, here is a B, and then here is a not A. All right. So not A, B, not C goes into this AND gate. So it's not A and B and not C. Okay. So this one expresses the first term, right? So similarly for the second AND gate, this AND gate will then express not A, B, C. And then this third AND gate will express A, B, not C. Okay, so if you check the where the connector is, you will then understand what goes into the AND gate. Okay, and then in the end, all these three terms are ORed. Okay, so that's where the summation of all the products will come in. All right. So now we have seen the three ways of expressing the combinational circuit or the function, if you want to call it. So we have the gates. You can express it using gates. You can express it using the truth table, and you can also express it using the Boolean algebra function way. Okay. Yeah. So I hope that is clear. All right. Now, sum of products, simple, right? It's pretty straightforward, right? Sum of product is something and something and something, or something and something and something, or okay. And then you just pick out all the ones from the truth table, okay? So if there are three ones here, if there are three ones, that means you have three terms in your function. So well, very straightforward, easy enough. Yeah, okay. Okay. Now, product of sums is a little bit more tricky. Okay, a little bit more tricky. Why? Because we're going to look at the zeros. Okay, we pick out all the zeros. We pick out all the zeros. So how many zeros? There are 5 zeros. Okay, so there are going to be 5 terms here. 5 terms, and all these 5 terms represent not F. Okay, it represents not F. Earlier in the sum of products, the terms, we pick up all the ones, remember? We pick up all the ones. When we pick up all these ones represent when F is true. That means we're going to if you notice the formula, here is F. Okay, F is blah 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 blah. So we are picking out those terms when F is true. But in product of sums, we're going to pick up where the F is not true. That means your function will be, it is not true when all the 5 terms. Okay, so if you look at the bottom of the slide, it is not F equals to, and then we pick them out. Okay, see, this term is not A and not B and not C. Okay, so not A and not B and not C. Okay, and then similarly for the second term is not A, not B, C. Okay, it's not A, not B, C. Right, and so on and so on and so on. So we express not F. And if you notice, this one, you look at the bottom, it is still in sums of products. Okay, sums of products, which is not what we want yet. Okay, not what we want yet. What we want is product of sums. That means we want it to be something something or something or something, and something or something or something and so on. So what we're going to do? We're going to do De Morgan's theorem. Why? Because if you notice this one, all the functions are in, all the terms are in ands, right? Not A and not B and not C, then or, right? So when you want to change it to ors, remember we can use De Morgan's theorem. Okay, so these are some basic identities. So remember this one. This is De Morgan's theorem, one of the identities. So if you have not X or X or let me let me say it again. If you have not X or T or Z, then you can express this as not X and not Y and not Z. So the not is broken. Okay, so that is De Morgan's theorem. The other way around is also true. If you have not X and T and Z, you can then break the thing to become not X or not Y or not Z. Okay, so that is De Morgan's theorem. So let's rewrite the function not F. So remember, not F was originally expressed in sums of products. Now we see how we can convert it into product of sums. Okay, so this not F, we then make it F by transferring the not into the other side of the function. Okay, and then we do De Morgan's theorem. All right, so in the end, we break this, we break the not. Okay, we break the not, and then this and, sorry, the or is converted into and. Okay, so that's De Morgan's theorem. Okay, one time. But if you notice, inside, it is still ends. It is still ends. So now we want to break the inside as well. Okay, we want to break the inside of those things. So we apply De Morgan's theorem again. So we can break this knot. Okay, so we broke the knot already. And then here, the and becomes or. Okay, the and becomes or the and becomes or this and will become or. Okay, and so on and so on. And of course, not A is actually A. Not B is B. Not C is C, and so on and so on and so on. Okay, so in the end, we get F equals to something or something or something, and something or something or something and something. So it becomes product of sums. Okay, so that's how we convert convert the truth table, which we initially express as sums of products, but not F. Okay, not F, sums of products, and then become F, product of sums. All right, so that is how we do the conversion. A couple of chat messages. Can we put input A, B, C horizontal? What do you mean by? Oh, you mean the circuit? Is it when you draw the circuit? Yeah, you can draw it any way you want. Okay, if A and B horizontal, then F will be at the bottom. That's fine as well. Okay. How many max input can be in this? Okay. It depends on the question or depends on the function. Here, in the sums of products, and now in this example is three variables. So you have to have your AND gate accepting three variables. Okay, so there's no fixed number of inputs that the AND gate can receive. Okay. So why do we look for zeros rather than ones for product of sums? Okay, that is just the method on how to, okay, let me go back to that slide. Product of sums. Okay, so but that's the idea of having product of sums. It's just the reverse of sums of products, right? So we look for zeros. Why? Because that is the method we convert the sums of product into product of sums. That is just the method. So that's why we collect the zeros. Okay. Because if you notice, if you collect the ones, we are collecting when F is true. Okay. And if you notice earlier when we try to do the okay, in sums of product, we collect the ones. Why? Because all those terms is true for the F. F will be true. As you see when we try to do the example here, when we try to do this working here, when we collect the ones, it works when it's sums of products, when we collect the ones. When we collect the zeros, it's the other way around. It won't be true for F anymore. So that's why in product of sums, the other one, we collect the zeros. Okay, so that's the way we work around it. We will take not F. I think that's the reason. Yes. Yeah, we're taking the not F. So after that, we convert to F. Yeah. So it's basically reverse. Now, not exactly a reverse, but how shall I say? It's not exactly a reverse. Why? Because we are using the not f just to express it as sum of products first. Okay, then we get f, and then we change the sum of product to product of sums. That's what we want to achieve. Okay, so it's not exactly the reverse of the function, but yeah, it's something like that. It's something like that. Okay, it's a yes and no thing. Okay. Right. So circuit-wise, it will look something like this. Now, this is already simplified. It's a little bit simplified. Why? Because there are no not gates involved. Okay. So if you notice, all the knots, the not A, the not C, the not A, not C, and all that. There's no not gate there. Okay, so it's simplified a little bit already. Okay, but if you want, you can still do the, or rather, ideally, you should still draw the full set of diagrams. Okay, right, and then at the bottom is the function f. Okay, function f, whereby A or B or C, blah 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 blah, and all that. Okay, so when do we use sums of products, and when do we use product of sums? Okay, one way to look at it is to see which one has more ones or which one has more zeros. Why? Because you see, in this particular truth table, okay, in this particular the same truth table, it has fewer ones and more zeros. Correct. So if you look at it, when you do sums of products, your function is shorter. Why? Because you only collect the ones, and since we have fewer ones, the function f will only have 3 terms, and therefore it is shorter. Okay. And if you do product of sums, notice that you're collecting the zeros, so you have 5 terms, and eventually your f will be, have 5 terms. It's longer. So in this case, it might look sensible to actually choose sums of products, because the function will then appear shorter. The circuit will have fewer gates, and so on. Okay, so that's one rationale. Okay. Yeah, so that's one reason of the choice between sums of product and product of sums. The other consideration is depending on what gates you want to use. Okay, depending on what gates you want to use, and which one is easier, which one is more, but what do you want to achieve lah, basically. Okay, but of course, ultimately we want to implement the function with just one type of gates only, either the NAND gate or NOR gate, which is again another issue altogether. All right. So, but ultimately here, you have all these, functions that are long or functions that are short. So ultimately, we want to have something that is simpler. Okay, like in this case, if a product of sums have fewer terms, we want to go for that. So that's one potential choice. But the other consideration that you want to take is actually to do simplification. Okay, simplification. You have possibly 3 terms, 4 terms, 5 terms. But if we can reduce the number of variables that are needed, that is also possible as well, because you don't want to consider so many so many the number inputs. Of variables. So one way of you mean having something simpler? Circuit, is it when you, is either by choosing a simpler product of sums or sums of products, or to do some form of simplification to the entire function, here, right? Okay, so here now, into this simplification can be achieved in various ways. Okay, there are various type of algorithms, zeros, and rules of thumb, or whatever. You can even use algebraic simplification. If the product of that means based on all those identities that we learned earlier, okay, we can then use those identities to do simplification. Why? Because there are other methods zeros, as well. There are 5 zeros. In this particular course, we will cover, so there are going to be 5 maps, the zeros, Karnaugh maps, and also the Queen-McCluskey's tables, right? If you cannot remember all, try to. If you cannot remember all, then you probably want to remember at least algebraic simplification and also Karnaugh maps. Okay, because Karnaugh maps is well popular. Okay, it's a popular method, and many syllabus covers Karnaugh maps at least. Okay, now let's first look at algebraic simplification. Okay, so basically we use the Boolean identities to reduce the number of elements, or to reduce the number of variables, and you want to do some form of shortening, whatever. So that is algebraic simplification. So yes, let's look at an example. So use the basic identities to reduce the Boolean expression to one or fewer elements. Okay, so let's look at this example. F equals to not A, B, not C, and blah, 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 blah. Okay, and of course, when you implement this circuit, you implement this function, the circuit will look like the diagram at the bottom. Okay, um, so can you all try? I don't know, because you have been exposed to some of the identities already. So why not give it a try? Just try. Right or wrong doesn't matter. So just try to use the Boolean identities to try to reduce this function. Okay. Take your time. I'll give you 1, 2, 3 minutes until I until I cannot wait anymore, or something like that. See what you get. Okay. See what you get. If you can, you can use the chat box to just type out the function. Otherwise, you can share your screen or something. You can write it out on paper, okay, and then share your screen or something. Okay. So I give you a couple of minutes to think about this, and I will then share my solution with you. Okay. Going through the chat box. Let me see. No, continue trying. I'm just trying to answer some of the questions in the chat box. Okay, going through the chat box, are we going to be asked to draw the gates? Uh, for this exercise, yes, I think eventually I will show. Yeah, if you want, you can draw the gates also. For those of you who have gotten the simplification, you can choose to draw the gates. But if you want to ask about exam questions, definitely. I mean, it's a very popular exam question. You simplify already, then show the gates. Yeah, it's also a popular exam question to draw the gates. Okay. Dinesh, you have a sample. You have your solution there. Okay, good. We will see what others come in. Okay, then afterwards we will discuss. Okay, some hints to your attempts. Tenacious solution can be further reduced. Okay, it's a good attempt that you have brought out the b to the side. Okay, but inside the bracket, you can still simplify further. Okay, Shasha's solution looks pretty good. Looks pretty good. Okay, it's even shorter than Tenacious. Um, Hazim's solution is similar to Tenacious. I think inside you can simplify further. Okay. Yeah, the rest looks almost there. The rest looks almost okay. I think we can continue. All right. Let's discuss the solution here. Okay, all your attempts are not bad. If you scroll through the chat box, it's a very good attempt. Okay, good. Right. Okay, so the working here now is the B can be taken out, okay, based on the identities given. So basically the B is taken out and then all these are then replicated lah. Okay, AB, not AC and also A not C. Okay. Now, um, we have chosen to replicate this one. Okay, this not A and not C. We can pretend that it is here. Okay, not A, B, not C. Why? Because A or A is still A. Okay, it doesn't change the truth of the function. So to help in the simplification, we have chosen to replicate that particular term again, right? And then we have removed B to the side. Okay, we have removed B to the side. And then what happens here is that we again we push certain similar terms to the side as well. So here we have taken out not A. Okay, so not A will then cover these two. All right. So this not A has appears both sides, right? So then we have taken out not A, and then inside here is not C or not C. Okay. And the reason why we want to replicate this not A, not C, B was so that we can uh, take out this not C to the side. Okay. So we take out not A, not C to the side. And then inside here, we have not A or not A. Okay. So that is one of the reasons for doing that. And then since not C or C is always true, right? Not 0 or 1 is 1, and similarly not A or A is always true. Okay, so in the end the solution here is B and not A or not C. Okay, so so I think among all the solutions that are posted on the chat, Shasha's one looks the closest to my proposed workings. Okay. Now again, you might have other ways of doing the working, and notice also, to help in the simplification, your use of the identities must be a little bit creative. Okay, if you follow, very rigidly, you might not be able to get the simplest possible. All right. So the creativity here comes from adding the term. Okay, when you add a term and you or the term, especially when it's the same, you actually don't change the truth of the function. So it's no harm adding extra terms that will eventually help you to simplify it further. Okay. I used De Morgan's law in the first place. De Morgan's law. How to decide what extra term we can add? Okay, how to decide what extra term we can add? That one I cannot tell you. Why? Because through experience, you then add extra terms that will help you. So in this case, we are adding the extra terms so that we can we can remove one of the variables out and then do the bracket. Okay. Yeah, creativity. That's a very good explanation. Yeah. So
Doctor,
I think I've yeah. Sorry.
uh, can you give us more hints about creative solutions like this? Now we have a method to add extra not harming term. Is there another way if this doesn't work in another situation?
Okay, I put it this way lah. If you didn't add the extra term, you might arrive at a solution that is less simplified. But that is not wrong.
Yes.
Okay, I mean it's just how you put in extra things so that it will help you in doing the simplification further. So if you didn't add the extra term, you would probably you probably stop at where I think Tinesh and a few others of you who had the bracket inside without further simplification. But that's not wrong, right? But that's not wrong. But it's not the simplest that you can achieve lah. Okay.
Mhm.
You
Terima kasih, Doctor.
indicate. Sorry again. Shazim, is it? Hazim, sorry, Hazim. Any other
Yeah.
things?
Terima kasih, Doctor. Thank you very much.
Oh, you're welcome. Okay, Shahid, you said that you use De Morgan's theorem. I don't know how you mean by De Morgan's theorem. You mean you expanded by De Morgan's theorem? That means you use something like this, is it? F equals to you did this. How do you use De Morgan's theorem here? That means you use not A or B or not C, something like that, is it? And then you also did I don't know, something like that. But I do not know how would that help to simplify this particular function. Okay. Shahid, you put okay, let me just show on the screen. Not A, B, sorry, not A, B, not C. And then you said this is A or not B or C. Yeah, that is possible. Okay. But how is this simpler? It looks more or less the same as what you started off with. But by simpler means you either reduce the number of terms or you reduce the number of variables and so on. You got 1 plus not B after. Okay, maybe if you like, you can either take a photo of it and share it with me on Telegram. Then we check it together. Okay. All right. Okay, another question here. Does not AC equals to A not C? No, I think it's totally different. Okay. A not AC is not the same as A not C. All right. Yeah, okay. I think I've answered the questions from the chat box. Yeah, okay. All right. So I hope everybody can understand some basic elements from this particular example. Okay. So after we have done the simplification, so this is the function, right? F equals to B, then you have the N, not A or not C. So the gates, when you have the gates, then it will look something like this. Again, of course, this is simplified. What actually should be done is you should have like A, and then you have this line going in, and then you have another one with the NOT gate, right? Yeah. So you can expand the thing more more simply lah, but this one is already simplified. So if you notice the gates look like this, but the original one looks like this, which is more complicated, no? Yeah. So yes, so with algebraic simplification, we have managed to simplify the function. and that also reduce the complexity of the circuit lah. Okay, you don't have to have so many gates in your solution, right? Okay, I think before we go into Karnaugh maps, I think it's a good time to take a short break. All right. We will resume at 9 o'clock. Okay. We resume at 9 o'clock. We take a short break now. Okay, I hope most of you are back. We will start very shortly. Yeah, thank you. Okay, welcome back. We will now resume the lecture on digital logic. Okay, where we left off before the break, we were basically talking about simplification, and we discussed algebraic simplification. Okay, so that means we looked at how we get a function, and then we used different algebraic or rather Boolean identities to simplify the function, and that actually resulted in a simpler circuit, a simpler function. Okay, right. So we will now try another method. Okay, it's what we call Karnaugh maps, and it's basically a convenient way to simplify Boolean functions with a small number of variables. Okay, a small number of variables. Um, it can simplify functions up to four variables quite easily. Okay, quite easily. But as it goes beyond four variables, when you go into five variables, then it gets more and more complicated because it involves 3D, 3D. Later, I will show you why it's only suitable up to four variables. Now, basically, Karnaugh maps arranges the variables into squares. Okay, it is a very diagrammatic way of simplifying the function. Okay. Now, so basically, how we go about doing the Karnaugh maps is we arrange the squares to represent the variables. Okay, so that means if you have, let's say, two variables, we then need four squares. Okay, because according to Karnaugh maps, we need 2 to the power of n number of squares to represent the variables. Okay, so if your n is, let's say, two variables, then you need four squares. If your n is three variables, then you need eight squares. If your n is four variables, we need 16 squares. Okay, 16 squares. And how we arrange the variables is the variables must differ by one digit side by side. Okay, so when we arrange the squares, when we label the variables, we label them, okay, in this case, it's two variables. So it's 0, 0 and 0, 1. Why? Because they differ with one digit. Okay, so in this case, if you, sorry, on a, okay, if you look at these two terms, okay, they differ by one digit, this one. Okay, so side by side, they differ one digit. And then if you look at these two, okay, again, side by side, they differ in one digit in the sense like they only differ in these digits. Okay? And then again, if you look at this one and this one, they differ again in only one digit, which is these two digits. Okay? So if you notice, this is not according to the order of increasing value. It's not 0, 0, 0, 1, and 1, 0, 1, 1. Okay, this is not mathematics. It's not ascending order. Okay, but this is a method to arrange the variables side by side so that they differ in one digit. Okay, so remember, Karnaugh maps is always 0, 0, 0, 1, then 1, 1, then only 1, 0. Okay, very important to remember this one when we solve problems using Karnaugh maps. Okay, okay, and then each square, okay, each square that we want to draw, we have to represent the terms in sum of products. Okay, that's very important also. It must be represented in sum of products, which means it must appear in this format, A, B, C, or A something, not B, C, or something, something. Okay, so it must be in that format. Okay. Okay. So basically, the most straightforward way is actually to look at the truth table. All right. When you look at the truth table, then it's easy to convert it to Karnaugh maps. Or if you have something that is already in SOP, sum of products, then also very easy. Now, if you happen to have a Boolean function that is not in sum of products, then you have to change it into the standard form. Okay, that means standard form meaning sum of products form. So earlier, when we simplified already, we got this, right? Okay, so you can, of course, this is already simplified, but we cannot do Karnaugh maps in this kind of format. Okay, we cannot do Karnaugh maps when it's all all over the place. Okay, it has to be in sum of products form, right? For Karnaugh maps to work. Okay. So these are some examples of Karnaugh maps. How do Karnaugh maps look like, and how do we, build the Karnaugh maps based on an algebraic function or from the truth table? Okay, so let's look at the example A. This A example, and then this is the function that we want to express. Okay, A not B or not BA. So if you notice, this is already in sum of products format. Okay, sum of products. And since there's only two variables, we prepare 4 squares. Okay, 4 squares. All right, and it's lengthwise. That's the standard way of drawing. You want to do it this way also can, but let's learn it one way first. Okay, all right. So yeah, so 4 squares, and if you notice, we label the squares 0, 0, okay, then 0, 1. And then careful, this is 1, 1, and then 1, 0. Okay? And basically what this means is that the first variable, the first one here is actually the A, and the second one here is actually the B. Okay? So in this case, let me see. These two squares will cover the A, and then these two squares will cover the B. Can you see? You notice this one, you see this first digit is an A, and this first digit is an A. So these two squares on the right side of the two righter squares will cover A when A is true. All right. And these two middle squares, if you notice, the second digit here is a 1, which means those two squares in the middle will represent when B is true. Okay. Now, then the other squares, which are not A and not B, they will then represent not A and not B. Okay. So that means these two squares are for not A. Okay. And then these two squares, this one and then this one, will represent not B. Okay. Let me clear that for a moment.
Victor, can you repeat, because this is very confusing?
Okay, let's look at this example now. I think with the example, it will be clearer. Okay, look at the first term, A not B. Okay, A not B. So A, it must be either this one or this one. Okay, but here now you want not B. Not B is this one, you see, is not B. So therefore, we put a 1 here. So that 1 there represents A and not B, which is true because A not B is 1, 0. Okay, the A is a 1, the B is a 0. 0 is not true, I mean not B. Okay, and then this other one, it's not A and B. Not A and B, which is a 0 and a 1. So we look for 0, 1, and then this is a 1. Okay, so when you have a function like that, an example function f like that, how you draw the Karnaugh maps, that's how it's 1 and then 1 on that side. Okay?
Yes, Doctor, now clear.
Now clearer. And if you want if you want me to complicate you again, so again, I just want to repeat. These two squares will cover A. These 2 squares will cover not A. Okay, because if you see these two A's here, are 0, so there's not A. And then yeah. Wait. If you look at this one, sorry?
Yes, Dr. Win. In this, when we have two variables, the A is always the first bit to the left.
Yes.
So
And
the
then,
first two ones represent the not A, and the second and the one on the left, two on the left, represent the positive A or the A.
Yep.
Because it's one. Yes, I get it. Now I get it.
Yeah, so that's only for two variables, huh? Okay. Now let's look at the example for, okay. So let's look at the variables. Let's look at the Carnot map for 3 variables now. This example B. So if you see, this is the function, and this is also the truth table, the same truth table that we saw in the earlier examples. Okay, with remember the example with 3 f's that are true. Okay, so that's why we have 3 terms here: 1, 2, and 3 terms. Okay, so here is 0, 1, 0. So we look for 0, okay, and then 1, 0. So this is the one for this first term. Okay. For 3 variables, again, this is how we draw it. We do the variable A as the rows, and then B and C as the columns. Okay. And this will also mean these 2 are for the B, and these 2 are for the not B. Okay. And then these 2 are for C, and then this one and this one are for the not C. Okay. Now, how you look at this is just look at the position of the zeros and ones. Okay, that will tell you which part is B, which part is not B, and which part is C, and which part is not C. Hamatsu is binary Sudoku. Yeah, something like that. Okay. All right. So this is how you draw the Carnot maps. Okay. If it's 4 variables, that means you're going to have 16 squares. Okay, you're going to have 16 squares, and it's the same concept. It's just that now on the left side will be A and B. Okay, and then on the columns you have C and D. Okay, and this particular map, okay, the grid or whatever you want to call it. So this is where we show which squares or which columns or which rows represent which variable. So this is the A, this is the B, this is the C, and this is the D. Okay. Then anything else outside of that would be not A, not B, not C, not D. Okay. So I hope everybody can understand how to plot the Carnot map based on the function, the algebraic function, and also the truth table. Okay? Right. I hope this one is easy enough. So we only use the ones. Yeah, we only use the ones. Why? Because we need the functions to be expressed as sum of products. Okay, sum of products. We can also do it product of sums, but then again, that will be in the not F. Okay, it'll be not F, and later we need to convert it again. All the De Morgan again. That's a bit more complicated. But I think we start off. Okay, to start off, let's do sum of products first. Okay, to represent all the ones. Okay, the fourth one is confusing. Which fourth one? The D, is it? Is it the one labeled D? D. Now, actually, D is not a Carnot map. It's just a summary of which variables are true and which variables are false. All right. Just like earlier, for the 2 variable one, I said this is A and then this is B. Okay. So, but if you have 4 variables, if you have, just a minute, somebody's mic is turned on. Okay, if you have 4 variables, then this will become the A, this will become the A, and then this will become the B, this will become the C, and this will become the D. I mean, this is which rows cover. Why? Because, okay, let me do this. This is, where's my pointer? This will be 0, 0, 0, 1, 1, 1, and 1, 0. Okay, so if you notice, this 1, 1 here are for A. This 1, 1 here is for B. Okay, so that's how the things are labeled. So this is 0, 0, 0, 1, 1, 1, and then 1, 0. So if you notice, this one is for the C, and then these ones are for the D. And so that's where the variables are true in for which rows which A and B are true, and for which column which C and D are true. Okay. I hope you can okay, doctor. Okay, yeah. All right. So Karnaugh maps plotting, I hope all clear. Why? Because in the next few slides, we're going to talk about the simplification. Okay. Now, how do we use the Karnaugh maps to simplify the function? Okay. Now, already the principle here is that any two squares that are next to each other will be different in one variable. Okay. And if both the squares have an entry of 1, that means something can be done with it. That means they can be either be merged to eliminate something. Okay? So whenever you have two variables, when you have two ones side by side, it means that they differ in only one variable. Okay? And since they differ in only one variable, the variable that is different can actually be discarded. You understand? You see, the way the squares are arranged, they are all different with one variable side by side. Okay, remember? Just now when I tried to explain, I don't know where. Yeah, you see from this one, from 0, 0, 0, 1, 1, 0, 1, 0, 1, 1, and 1, 0, all of them are differing one variable when they are side by side. So if you plot the Karnaugh maps and you see two ones that are side by side, which means those two terms they differ in only one variable. Okay, and there will be another variable which are the same. They differ in only one variable. So that variable which is different can be removed. Why? Because they are disturbing they're disturbing the unity of those two terms. Okay, wait. Before I confuse you further, okay. So that is actually the principle. The two ones that are side by side, okay. For example, if you have four squares, right, and you have one here and one here, right? Now those ones will represent a term, and those terms will differ in only one variable. Why? Because they're side by side. Okay, and since they differ in one variable, that means that variable that is different can be removed. Okay, so that is the principle. Now let's look at an example. I'm sure many of you are confused by the verbal and textual explanation, but let's just forget about that. Let's look at an example, and hopefully that will be simpler. Okay, let's look at this simple example. If your function is f equals to not a, b, not c, d, which is this term, okay, it means it's 1, 0, sorry, 0, 1, 0, 1, okay? So it's 0, 1, 0, 1. All right, so it is this term. Okay, hopefully that's clear. Then this one, the next term here is 0, 1, 1, 1. Okay, so it's 0, 1 again, 0, 1, and then 1, 1. So it is this term. So these two terms, there's not A, B, not C, D, or not A, B, C, D. So these two terms, they are side by side. Okay? And since they are side by side, they differ in only one variable. Okay? Which variable is different? See, not A and not A, same, right? B and B, same, right? D and D, same, okay? Which one do they differ? They differ in the C. One is a not C, and then the other one is a C. Okay, so that's the beauty of Karnaugh maps. When two of those terms are side by side, they only differ in one variable. Okay? And yes, Shahid, we discard the C. Okay? So the C is the one which is disturbing, which is disturbing them. So we remove the C. All right. So in the end, the simplification is this one. Easy, right? Instead of what Boolean identity, which one to remove, factorization, blah blah blah. Actually, it's not factorization. It's it's some form of whatever. So yeah, so this is how Karnaugh map works. Okay, and if you also notice, if there are two terms side by side, okay, you can remove one variable. Okay, all right. So if you are two terms side by side, you can remove one variable. Okay, what other ways can you have side by side? It's also possible to wrap around. Okay, like for example, if you have one here and then this one at the bottom, so it's actually wrapping around. Okay, you're wrapping around. Actually, is joining the other side. Yeah. Oh, okay. So it's actually the other side, and they also still differ in one variable only. Okay, correct or not? They only differ in one variable. You see, on this row, both are 0 and 1s. Okay, 0, 1. But if you notice from on the row side, this is 0, 0, and then this is 1, 0. So yeah, they differ on the variable A, isn't it? They differ on the variable A. So if you notice, this again is function not A, not B, not C, D, or A, not B, not C, D. Okay, so what do they differ? Okay, wait, which one is the same? Not B is the same, not C is the same, D is the same. So they differ in the A. One is not A, and one is A. So we can say bye-bye to the A. Okay, right? So that is like overflow. Shahid say like overflow. Interesting observation, but it's not. It's a wrap around. So imagine if you have a piece of paper, you fold the paper into a circle, like that. Yeah, yeah, overflow. Okay, so does it matter if so if it matter that the number in the box don't sit side by side? Okay, if they're not side by side, which means we cannot do the simplification. Okay, like for example, okay, let's where is my okay? Let's look at this. Let's look at this table here. If you have, let's say, one here and then one here, they are not side by side. Cannot do simplification. Okay, you cannot do simplification if the numbers are if it's separated. It must be side by side. Okay.
Even with Boolean
Same thing.
algebraic, right?
Sorry again.
Even with Boolean algebraic, we cannot simplify when it's not side by side in the Karnaugh map.
You can try, but I think it cannot be simplified. Okay, you can try, but I think it will not work.
Yeah, Karnaugh maps is now the best way now to simplify.
Yeah, only if you can represent the function in SOP.
Okay. Yes, some
Yeah.
products.
Correct.
Okay.
All right. So yeah, so the other example is also true. You can wrap around row wise as well. Okay, it will work as well. Okay, so similarly, this function, you can remove C. So again, all these examples are shown if there are two variables side by side. Okay. So what about other forms of combination? Let's say not only two, what about 4, 8, and so on? So if you have 2 to the power of n variables that are side by side, you can then eliminate. Okay. So we can have 2, we can have 4, no 6, 8, or you can even have 16 and so on and so on. Okay, but since we only have 4 variables, okay, we only do 4 variables, we don't do 5 variables. 5 variables is 3D, is more complicated. For those of you who are interested, if you Google for Karnaugh maps 5 variables, then they will explain to you. It's going to be in 3D, blah blah blah. It's more complicated. So for us, we go to as far as 16 possible side by side. Okay, why? Because we have 16 squares. Okay, 4 variables. So your grouping can be in 4, can be in 8, can be in 16, or whatever. Okay, so in this case, for this example, Okay, this is example D already, yeah? Example D, yeah? So we have 4 terms here. Okay, we have 4 terms here. That means originally, F equals to something, 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 or something, something, or something, something, or something, something. Okay, so you have 4 terms. So what is the simplification of these 4 terms? Now, when you have 4 terms side by side, you can remove 2 variables. Okay, 2 variables. Now, how do we go about that? Let's look at this. Now, let's look at this row, of course. Now, all these 4 variables, okay, this 1, 2, sorry, 1, 1, 1, 1, it's all side by side, right? Now, all of them are not A, correct? All of them are not B, correct? Right. All of them are, okay, let's look at C now. Are all of them C? No. Some are in C, some are in not C. Okay. What about D? Are they, sorry, are they all in D? No, because some are in not D. Are all of them in not D? No, because some of them are in D. So the C and the D are causing confusion here because all 4 of them are neither C nor not C and also neither D nor not D. So we remove the C's and the D's altogether. Okay. And we keep only the not A and not B. So from these 4 terms, if you can have 4 variables side by side, you can simplify it to just this one term. Beautiful or not? Powerful or not? Okay? So that's Karnaugh maps. Let's see. The numbers must wrap around or they are adjacent. Yes, correct. Yeah. Okay, so that is one example. Now this is another example here. 4 variables. Now remember, they all must be side by side, okay? And next to each other. Like this cannot work. This one, 1, 1, 1, 1. It's not tic-tac-toe. Oh, I win. No, it must be really, really next to each other, not diagonally also. Okay? Tic-tac-toe. All right, let's look at this one. So how do we simplify these 4 terms? So again, this one would have been something F equals to A or or okay, 4 terms, right? That's why you get the 4 ones there. So so we ask ourselves, is this in A or not? Are these okay, we must look at all 4. All 4, are they in A or not A? This is A and this is not A. So some and some. So to decide whether it's A or not A, we cannot decide. Okay, so it's a problematic variable. What about B? Okay, this is B, and then this one is not B, and this is not B. Okay, so all those 4 variables, are they in B or not B? So all of them are in B. Okay, so B is no problem. So we can keep B, but we eliminate A. Okay, because A is, one leg in, one leg out, that kind of thing. So we eliminate A, but we keep B because all these 4 ones are inside B. All right. Now let's look at the C and the D now. Where's my pointer? Okay, this is C, and then this is D. Oh, sorry. Yeah, mistake. All right, this is C, and then this is D. All right, so we decide now, are those 4 inside C or are they outside of C? All right, so we can see that it is outside of the C. So we can keep not C. Okay, now let's ask ourselves about the D now. Are all those 4 ones inside D or outside D? it is one leg in, one leg out, right? So D is a problematic variable, but C is fully not C, all right? So here we eliminate the A, we eliminate the D, okay? And we can keep B and we can keep not C because they are clearly in not C. So in the end, we get B not C, all right? Yeah. And similarly for F, this example F here, again, the function has, 4 ones there, right? So originally it would have 4 terms. And then here, we can do the grouping wrap around also, okay? So if you notice, this one are clearly in B, that's why we can keep the B. And then clearly in not D, okay? Because D is the one in the middle. So outside of the ones on the left and on the right, these are the not D. So that's why we can keep not D. Okay, so that's the beauty of Karnaugh maps here. Huh? What about 8 ones? Okay, so with 2 ones, we can eliminate one variable. With 4 ones, we can eliminate 2 variables. So if you have 8 ones side by side next to each other, we can eliminate 3 variables out of the 4. Wow, super power here. All right. So again, you have 8 ones, which means your function would have f equals to and 8 terms. Okay, but since now all these ones are side by side, we can group them all together and then we see which variable is the problematic variable. Okay, now if you look at the A's and the B's, it is clearly, okay, this is the A, right? And so they're all in not A, obviously. Okay, all in not A. Now let's look at the C's and the D's. So they are all covering all the 4 columns. So they are both in C's and not C's. They are both also in D's and not D's. Very problematic. They're all over the place. So C's and D's we eliminate. All right. And we eliminate B also. Why? Because B would have been the middle 2. And now all these 8 ones are both in B's and not B's. So we eliminate the B as well. So in the end, we are left with not A. Wow, just looking at this 8 ones side by side, we can already very easily say, it's only not A. Okay? And the other examples, I think they are self-explanatory. I think I don't have to go into detail. So this one, we are left with not D, and this one, we're only left with C. All right, Hannah, I hope you understand the use of Karnaugh maps. But this one, we are showing very, very simple examples, very clear-cut simplification. The real Karnaugh map is very messy. Okay, but anyway, this is the basic rules for the simplification. Okay, we look for the largest blocks of 2, 4, 8, or 16. Okay, right? The largest blocks. So if you have, okay, let me just.
If there is 16, there will be all different. A and B and C and D will be different.
Okay, let me show you. Okay, I understand what you're trying to get at. Ayo.
I don't know what it keeps doing this, not only with you, doctor, with a lot of lecturers also.
Yeah, because I think my fingers are a little bit sweaty, so it affects the sensitivity of the board. Okay. Right. So if you have 16 squares, and then all ones, is it? All ones. All ones. So all ones. Okay. So you can actually group all of them together, no?
Mm-hmm.
Okay. You group all of them together. Yes. So originally it's 16 terms. Okay, 16 terms, something and something and something, blah, 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 blah. Now, after simplification, what do you think is the simplified term?
Nothing.
Nothing? 0?
Oh, well, I think so. There will be a lot of there will be 4.
Okay,
I
there are
can't
a few
imagine,
responses.
doctor. I can't imagine 16 tabs.
Okay, there are a few responses in the chat. So that means this function is always true. Okay, always true. That means in your truth table, if you draw the truth
Will be
table,
all
that means there
one.
are four variables, A, B, C,
Yeah.
D, and then function F. Okay, so when you draw your truth table, 0, 0, 0, 0, and 0, 0,
Will also
0,
be one.
1, 0, 0, 1,
16
and
rows.
so on.
16 rows.
Now, all of them are ones. So that means this function is always true. Okay? Ones all around. Okay, so after simplification, you will get 1. Okay, that means it's always true. All right, so that's in the case
So
of
how do we?
16.
What term should we use in this this situation? Will it be A only? Will be B only? Or
No,
what will be?
there's no A's or B's or Z's. The answer will be 1. That means always
Oh,
true.
that's right.
Ah,
Yes, yes. One will cover all of them. Yes.
yes. Okay?
Thank you, doctor.
All right. Okay, so the back to the rules of simplification. So we look for the largest blocks. Okay, so that means if you have, let's say, okay, I just want to erase some of this. Yes. So if you have, let's say, eight squares all side by side like that, we make sure we get the largest. Okay, we get the largest possible. Don't for example break them up into, oh, I'll just these two are side by side. Oh, these two are side by side. Oh, these two are side by side, and these two are side by side. In the end, you get four simplified terms, right? But no, we can actually group it into the largest possible that you can get. Okay, the largest possible 4, the largest possible 8, and the largest possible 16. Don't break them up into smaller groups. Okay, so look for the largest. All right. And what else? Yeah, draw a loop. Yeah. So this is the what we showed in the examples is what you should do lah. Okay, but this is just a textual explanation of what we have just done. So I hope you understand. All right. What about in cases where there's overlapping? So let's say, for example, if you have these three variables here, sorry, three terms that are side by side, but they overlap. Okay, not a problem. So in this case, we express them as two separate groups. Okay, so one group simplify, and then the other group also simplify. We get two separate simplified terms. Not a problem. Okay, but if you have groups that are overlapping with each other, like for example, now you have three groups. Okay, you have three groups, but one of the groups can be incorporated in either one. Okay, so in this case, we eliminate the one that is belonging to both. Okay, so we only keep two simplified terms. I'm not saying that you cannot do this. You add blah, 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 blah. Again, another simplified term. But again, if you do that, then you have three terms. Okay. Why you have three terms when you can have two terms, right? So in that way, you eliminate the one that is redundant. Okay. How about, okay, let me see some messages here. How about if all ones is not side by side? How is it possible if it's not side by side? If you're talking about all ones, if it's 16 squares, okay, if it's 16 squares all side by side, you can't have more than one group. Sorry, I mean, you can't have them not side by side. If all ones not side by side. So if you're talking about 16 squares, it's not possible to have the ones not side by side. All the squares will be filled already. Okay, maybe Shaudu, you want to explain what you actually mean, okay? But anyway, hopefully whatever is on the slide is okay at the moment. Okay, let's proceed. Okay, now in some cases, you might have don't care situations. All right, don't care situations meaning that not all the input patterns are taken into account. Okay, not all the input pattern are taken into account, or not all the input pattern are used in the function. Okay. Now let's look at one example here. The example of packed decimal or binary coded decimal. Now, in the decimal system, we have 10 numbers, correct? We have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 different numbers. Okay. So in order to represent binary coded decimal, we need to have at least 10 different patterns. Okay. And in order to get that 10 different patterns, we need 4 bits. If you only use 3 bits, you only have 8 different patterns, which is not enough to represent the 10 different the 10 different binary digits. Okay, so we need 4 bits. We need 4 bits to represent the binary coded decimal, or we call it the packed decimal. Yeah. Okay. So there will be some bit patterns that are not necessary to code the binary coded decimal. Okay, let's look at the truth table here. Okay, just get this out of the way. All right. So in this column, we want to represent certain digits. Oh wait. Okay, this input pattern, for example, this input pattern 0, 0, 0, 0. Okay, we want it to represent the decimal digit 1. Okay, so that means the binary value of 0, we want it to represent the decimal digit of 1. Okay, so don't confuse yourself. On the left, the ABCD is the binary code. The one on the right, the X or the WXYZ, that is the decimal value. Okay, the decimal value. So the if it's 0, 0, 0, 0, we want it to represent decimal 1. Okay, and then the others will then follow lah. If it's 0, 0, 0, 1, which means the value of 1 in binary, we want it to represent the decimal digit 2. Okay, so it's represented here. This is 1, this is 2. Okay, then and so on and so on. The binary digit, the binary value 2, which is 0, 0, 1, 0, we want it to represent the decimal digit 3, and so on and so on and so on. So after the 10 patterns, then we have all these other patterns. Okay, we have all these other patterns. So when you have a 1, 0, 1, 0, this is actually binary 10. This is binary 10. And supposedly, this will be 11, but we don't want already. There's no such thing as digit 11 in decimal, correct? So all these are all don't care. See, all these are labeled as D. Don't care, 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 don't care. All right. So no matter what are the input patterns, the output is don't care. All right. Okay. So how do we do a Karnaugh map simplification when you have don't care situations like that? Okay. So let's look at the simplification. And remember, each Karnaugh map is one function. Okay. So in this case, where is my pointer? Okay. So W here is a function. This X is a function. The Y is a function. And this Z is a function. Okay. So that means your W would be something ABCD or something ABCD or something ABCD. So W will be a function of ABCD. Then similarly, X also. X equals to something ABCD, AB or AB or not A or blah, 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 all the ABCDs. Similarly for Y and similarly for Z. So if you look at the bottom of the screen, you will see 4 different Karnaugh maps. Okay, 4 different Karnaugh maps for the 4 different W, X, Y, and z functions. Okay, and we do the same thing. Okay, we look at okay, let's look for w. So if you look at w, we have two ones. Okay, two ones and 1, 2, 3, 4, 5, 6. Don't care. Okay, so if you look at the Carnot map here, we have these two ones, okay, and 6 don't care boxes. Okay, now how do we do the simplification in this case? All right, notice that the ones are far away. The ones are far away and they cannot be grouped together. Okay, but we can make use of the don't care. Okay, now we only make use of the don't care if it helps in the grouping of ones. We only use the don't care if it helps in the grouping of ones. It can only be grouped with ones. Okay. So in this case, you see the don't care, you have 4 don't cares here, one whole row of don't cares. But we are not allowed to group them. Why? Because it's not important in the function. Okay. We also cannot use this 4 don't cares here. Again, because it is not important in the function and it's not helping the ones. Okay, it is not grouped together with the ones. All right. In the end, what can be used? Okay, let me just clear this a little bit. Okay, notice that you have a wrap around at the bottom here. Yeah, this one. See, there's a 1 here. There's a 1. And then there's some don't care here. There's a 1 don't care here. And then also there's a don't care here, and also there's a don't care here. But these 4 squares has a 1 inside. So those 4 must have a 1 there. The don't care must help the 1 to form the group. Okay? And then, okay, you still have 1, 1 here. Okay, you still have 1, 1 here. In the solution here, they didn't group that 1. But actually, you are still allowed to make a group here. Use this don't care, this one, to form one group here, which is also possible. All right. So if you have a situation whereby you have don't care values meaning that it is not important in the objective of the function, the don't care can be used to form a group provided the ones are also included in the group. Okay. You cannot have don't cares forming groups on their own. Okay, right. So similarly for function x, y, and z, we do the same thing. Okay. In this case, yeah, we don't just do this square. Okay, we don't just do that, but we can actually do a wrap around. Okay, we can do a wrap around on this side. So, and remember, there might be different combinations of groupings. Okay, you can, but just remember the grouping must be as big as possible. All right, that's the main objective. All right. Jintun has a message on the chat box, just like the BCD code. Yeah, binary coded decimal. BCD, that's binary coded decimal. All right. May I know what is BCD? Yeah, BCD is binary coded decimal. So binary coded decimal is just a way to represent numbers in how to represent decimal digits in a binary way. Okay, so if you want to convert them into a function or convert them into a circuit, then this is how it's potentially going to look like. Okay. I heard somebody trying to chat. Yeah.
Is there any kind of question like this when how do we know that we are arriving at don't care outputs?
Okay, you'll be told to you. You'll be told to you. The question will indicate yes, you can use don't care or whatever, or the question might show you a truth table like this, and then there will be don't care values there. Okay.
Oh, so you are going to present to us the truth value, and we extract from it the Karnaugh maps.
That is one possibility. That is one possibility.
One possibility.
Or for example, if sorry.
Yes,
or for example,
yes.
sorry.
Continue. Yes.
Or for example, if the question is about binary coded decimal and you have already filled in all the available patterns, and then there are some bits left over, then automatically you can treat the rest of the functions as don't care. Okay, so that's another way of looking at it.
Mhm. Okay, but I really don't understand how is 0 getting 1. What is this? This is really,
No, this is
how is
it's a
0?
representation. It's a representation. It doesn't have to be equal value. Okay, so that means when it's when it's 0, 0, 0, 0, it is a representation of the decimal one. It doesn't have to be equal to one. Understand or not? It's just a representation. It's just a
Oh.
representation. It doesn't have to have equal value. Okay, so that's what
So
we
when
mean.
we key into it okay, okay.
Yeah, it's just a representation. It's an example for this purpose of Karnaugh maps. Okay,
will be a function.
you may also have some implementation which says that a 0, 0, 0, 0, 0 also means zero in the decimal side. So you have 0, 0, 0, 0, for example, and then this 0, 0, 1, 0, 0, 1, 0 also it's possible. Then you do the simplification, see how it looks like. Okay, but this one is just given as an example to show the representation and the function and how to simplify the Karnaugh maps. Okay.
Oh, so
And
it
in
is
this
not the
case,
right thing. It is just
it
for
might not be
example.
the right thing. It's just a representation. Okay.
Okay.
Is the D symbol always located at the permanent box? Yes. I mean, if it's stated in the truth table and if that is the bit pattern, the input pattern, then it has to be in that box. Okay, for that function. Is this a fixed table? Not necessarily. As I was mentioning to Hazim, it depends on the function. It depends on the thing that you want to represent. Okay. So in the case of this one, we wanted to use it to represent the binary coded decimal. Okay. All right. I think before we go, let's try an exercise before we end the lecture. So use Karnaugh map to simplify this function. Okay. You can see the function on the screen. So quickly plot a Karnaugh map and then do the simplification. So as a tip, this one you have 4 variables. So we know that you need 16 squares. Okay. And then, yeah, do the grouping and see what you get. Okay. So once you have the answer, please shout it out in the chat box. Okay, very good. I see some responses coming in. Wow, very fast, you all do this. That means it's a very powerful method, right? And also you are very, very quick in learning. Very good. Okay. You guys are super learners. BD, 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 BD. Okay. Let's take a look at the answer. All right. So 16 squares. All right. And then we have 4 terms. So 4 terms, we can plot them in the respective squares. Okay. And since we have 4 squares side by side, yeah, 4 squares side by side, so we can make one big group. No need to make 2 small groups. Okay. So we have that. Sorry. So that one group there in the middle. Okay. So if you notice that this one is okay, in terms of A's, it is not clearly in A, not clearly in B, so we can eliminate A. All right. What about B? Is it? Let's look for B. It is clearly in B, so we can keep B. Okay. What about C? C is not clearly in C, not clearly in not D, so we can eliminate C. All right. What about D's now? It's clearly in D, but not in not D. Okay, so it's in D. So we can keep D, right? So in the end, the function is f equals to BD. Okay. So I hope everybody understands how to do Karnaugh maps. Any questions on this particular exercise? I hope it's clear. Okay, all good, eh? All right. Anybody else got any problems? Okay, I hope everybody is okay with this one. So Karnaugh maps is good with 4 variables. When it goes to 5 variables, you need 2 sets of 16 squares. So they need to be overlapped. And then it will become 3D. So very problematic. If you have 6 variables, you'll go into 4D, which we don't want to do. All right. We want to do, but don't worry lah. If Karnaugh map comes up for CST 131, it will be up to 4 variables only. All right. So the other method will be Queen-McCluskey's method, which we won't cover today. I will reserve that to next week's lecture. All right. So thank you very much for joining today's lecture. We will end here today. And yes, there's still one more tutorial group today afternoon. And I will try to release tutorial 3 by today. Okay. So so try the tutorial questions when they are available. And then I will see the last tutorial group this afternoon. And our next lecture will be synchronous on Tuesday, 2 o'clock. Okay. There's still one question about overlapping elimination. Yes. Okay. So in case you want to listen to the explanation, I'll explain again after we have ended the lecture today. Yeah. All right. So thank you very much for joining the class today. Bye bye. I will see you next week. Okay.